Okay, let's take a look at this problem. Implement try. For the try, we insert apple. Then we search, should return true. If we search app, should return false. App is not a word. But if we search for start with app, should return true. App is a prefix of apple. Then we insert app and we search app, we should get true. You may assume that all inputs consists of lowercase letters A to Z. All inputs are guaranteed to be non-empty strings. That means we only need 26. An array, node array of size 26. So let's first talk about what is a try. A try node is an array of a try node basically have two fields. One field is an array of pointers. Each array element is a pointer to another try node. Let's say try node. To another try node, or now. There could have some place we have another try node. So each position corresponding to a character. The first character is A, the second position is B's position, third position is C, so on and so forth. So the last position is corresponding to Z. So if we have a word apple, the insertion looks this way. We first create a node array, and we set the first position to now, the other position is first position to a trie node, try node, the other position or now, so that we know at the first position, we have this try stores a letter start with A. So later, if we add we add a new word called a cat, say we have a cat inserted, then we initiate this to a new try node. That means in this try we have a word start with C. And this try node is again this try node is also have a have a try node array, right? Have a try node array which is size 26, and if we are inserting apple, for this P we need to insert a new try node on P's position. So that means we have a word start with A followed by P, and it's still not ending. We have other node. The P is pointing to another node, which again is an array of try node, and we have ale, not a now, Again, this is a P. The P is not null. So you point to another trinode array. You guess what? The L's position is not null. And which again point to another trinode, the trinode of an array of trinodes. Okay, array of trinodes at the E's position, A, B, C, D, whatever, at the E's position, let's see. At the E's position, there is trinode, and this trinode, again, you point to another trinode array. At this point we don't care anymore. This is our last character. And this trinode, we don't care about the content of this trinode array. We looking for a marker, which is isEnd. If it's a Boolean, the marker will say isEnd equal true. Then we know, okay, this word end here. So later, if we are searching for this apple, what we are going to do is we first looking for A. At A's position, we find a node, then we follow that node. And next, this node have a node array. We're looking for P, and we find this node. This node have a node array. Then we're looking for the P's position, because that's our third character, and which lead us to another node array, and we're looking for L, which has it. Then we keep looking for another node. We're trying to looking for E. At E's position, we find a tree node, and we're looking at the Boolean character, which is isEnd equal true. In this case, then that means our last character E is landing on the ending node. That means apple is inside our trie. How about the app? If we are searching for app, what will happen? We find the first character is A. We find this node, then we follow this node, and we're looking for P. We find another node and we follow it. We're looking for P, and we find a node and we follow it. At this point, this is the last character of app, and we're looking for isEnd. In this case, it's false, and we know app is not in the trie, and we should get a search miss. However, if this is startWith, we don't care about this app. We don't care about isEnd or not, because we follow those node chains, and we find the app. We find the app. Oh, not here. Here, right? We find the app. This is found. So startWith should return 2. How about we search for apx? We search A. We find a link. So we go looking for P. Next, we are looking for X at X position. We get a null. Unfortunately, that means APX is not inside the trie. So we should return false. That is when searching, if we hit a null node before we reach the end, we should return false. We didn't find it. So we know this data structure. Let's create the trie. Here, public trie. We should first create a private static class like the trie node. Trie node have two fields. One is trie node array. That is our next link. That is equal to trie node array new trie node array. In this case, it is 26 character, and we should have a Boolean near the end. In this case, it's equal false. Those are default values. Okay, and for trie, we give a trie node root. This is a root node. When we created the trie, we just initiated root equal new trie node. Now insert. We have a word. What we are going to do is we should first get our first character. This will be a recursive call. So first, let's write a private void insert. We should passing a trie node. This is a node we want to insert. This is a node we want to insert under. And we have word, and we have an integer. Let's mark the character we are currently processing. So the first thing we want to do is we want to get the integer n. First we want to get the word char at n. This is char. That's -a. Give us an integer, and k, and into p. Okay, this is a position. We are looking for the next node. So here we have node, next p. For this node, we want to, now we find a trie node, right? Find a trie node, new trie node. this is next node. We find the next try node. So in this case, if next equal null, that means we don't have this node yet. So what we should do is we should create it. So we should say next equal new node, new try node. We just create a node, and next this node is we should initialize this node and next. Wait. Now the node next p next p should be this next node. Now the node next is set. Then what we do is we should keep insert into the node into the next node, and our word and n+1. So now we keep inserting, and before we do that, our exit condition we need. So if n equal word length, n equal word length, that means we just we have to return. We don't need to do anymore. We exhausted all the word. And one thing is, here we created this next node. The next node is created by default. The isEnd is false, so which is true for most of the cases. However, in some cases, if I'm processing the last word length -1, that means I'm just processing the last word. So in this case, the next isEnd should be set to true. Okay, then we should this should handle the insert, and now we can call that insert. We pass in the root node the word. Our starting character is at position 0. We have the insert. Now let's handle the search. Again, this is a recursive call. So let's do a private Boolean search. Again, we need a try node. We need a string, the same as before, word, and int m marks the position. So in this case, what we should do? First, let's gather the int position, which is word char at n -a. This is our position. Then we get the try node. On that position. So node next p that give us next node. Say if next that is null, that means we didn't find anything, right? We should return false, because we are missing. Otherwise the next node has value, so we should keep searching. We should return search next. Yeah, we're passing the next node and then the word and n plus 1. What is the exit condition? We have it. However, there are two conditions to consider. If we reach the last node, if n equal word, length minus 1 at this point, we need to detect if the next node, this node is end. If this is true, okay, then we don't have to explore further. This is a lost character we exam, so we should just exam the is end. If is end, then we found it. Otherwise we didn't find it. So this is our exit condition. We either return false before we reach the lost character, or we return the result of the isn't as a lost character. Otherwise we recursively call the search. So here let's call that function return search root, passing word, passing position 0. Okay, now startWith is quite simple. We should just do a private Boolean startsWith. I guess exactly the same. Not exactly the same, that most of them are the same, I would say. And then here startsWith, and this check is not necessary. If we reach the end, we just return true. Otherwise we are all set. Now let's call that function return startsWith root node, prefix, and 0. Okay, let's run an example. Let's insert apple. When we do the try, we create a root node, and then we insert an apple. When we do the insert, put it here, apple. Insert a, the root node, int position currently is at 0, and equal word length not true, so we got the position p equals 0 in this case. The node 0 is null, so we create a new node and this is not applied yet. So node next at position 0, we give it to this new node, and then we insert into this next node, word at the position 1. So this time we are at position 1. Let's add a P. We get a position of P, and again we got null. So we create a new node. This is not a match, so we give this new node none null value, and then we keep digging until we reach the E. When we reach the E, we find next equal null, and we create it this time. The word length -1. The lost character, so we set the next equal isn't equal true, and we assign this next node and we go dig one more level, which is here, and we are safely returned. Okay, for the search for apple, the same thing. We pass in an A, and we find position P. This gives us a null, so we go into here. This is not applied, so we keep digging until we go to E, at the letter E, and we find the next at a letter E, we check the next node. We check the is and is true, so apple should return true. For app, when we reach P, and we go into here, is next equal false, so app should return false. How about startWith? StartWith for app, when we enter here, we return true. So this should work. Let's run the program and see what happens. Okay, true, false, true, false. Oh, false. So search app, insert app and search app. Okay, insert app, try search app. To return true, actually it returns me false. Why is that? Search function let's examine the insert. Word length -1, if n equal word length. That's when we create a node. Word length -1, that's easy and equal to. Node next P equal next. If you already exist. Oh, I see. If you already exist, this will be skipped, so I shouldn't put it here. We already have that, so let me do it outside this loop on the insert. If I'm reaching the end, I should always set is end equal true. So this time the app should work. Let me run it. True, false. True, false, true, true. Okay. And the time complexity for insert, I need to, for insert a word, I need to go through each character. So the time complexity will be OW, which is the length of the word. And the space complexity will be, in this time, I created a 26 for, if this word is not exist, then I need to create a W node, trinode, W trinode. Each trinode will occupy 2 fields. So if we can treat the trinode as a constant, it will be proportional to the length of the word. So the space will be OW again. W is the end of the length of the word. And for search, the similar thing. The word, I need to examine each of the characters, so time complexity will be OW. Time complexity will be OW. Do I use the actual space? I don't think so, except that that quarter stack. So the quarter stack could be, the quarter stack length is also OW. So the space is also OW, because we need to dig in, walking down the trinodes, the recursive quarter stack. We occupy OW space. Startwith the same thing. The only diff is at the last step. So for each of the functions, time complexity OW, space complexity OW. That is this problem.